All of these cells that you see pictured here, they derive from a myeloid stem cell. And remember that myeloid stem cells derive from an even higher placed stem cell, like the king of all stem cells, a hematopoietic stem cell. The cell over here on the left, this pink one, is called a megakaryocyte. And it explodes into fragments to make platelets. And each of those fragments, they contain a piece of the nucleus. A piece, not an entire set of DNA. And it's these fragments that are called platelets. A single megakaryocyte can produce thousands of platelets before being destroyed or phagocytosed in the red blood marrow. Platelets are essential for clotting, and they only last about 10 days, so they have a pretty high recycle rate. High platelet counts might indicate a recent event, even if it's no longer ongoing, like a bleeding event. Blood clotting, which is also called hemostasis, it's a positive feedback mechanism like labor, right, where the stimulus gets enhanced and enhanced and enhanced. We usually think that negative feedback mechanisms maintain homeostasis, but actually here a positive feedback mechanism is used to do it. Platelets, what they do is they form a plug at a broken vessel site, and then they attract more platelets to create a temporary seal. And that creates like a platelet party, and that's positive feedback. The process of doing this has 3 stages. A vascular spasm, which is kind of like a tourniquet, just like clamping down on the area, and then a platelet plug formation. And then we go through with a process called coagulation, which creates a formal blood clot. We've previously talked about fibrinogen, which is a protein that's soluble in blood, and it becomes insoluble, turning into fibrin during clotting. And it's fibrin that forms this like mesh that traps red blood cells and creates a clot. Coagulation involves a cascade of reactions that finally end in fibrin production. There's a protein that's called factor X, and it plays a central role. And the final thing it does is it converts an enzyme called prothrombin to thrombin. And it is thrombin that converts fibrinogen to fibrin. Hemophilia, which is a bleeding disorder, it results from the lack of proteins necessary to activate factor X, right? If you can't activate factor X, then you can't use thrombin to convert fibrinogen to fibrin. Blood thinners like heparin and aspirin can prevent clotting by targeting thrombin, while there's something else called plasmin that targets existing blood clots. You know, I did read an article lately, though, that aspirin is not good for certain conditions like atrial fibrillation. Anyway, moving on. Blood clots can block vessels, causing conditions like myocardial infarctions, heart attacks, or pulmonary embolisms, PEs. Coronary thrombosis blocks blood flow to the heart tissues, causing tissue death. And pulmonary embolisms occur when clots block lung capillaries, depriving those lungs of that, or depriving blood in the systemic circuit of oxygen and potentially leading to oxygen-deprived blood reaching your brain and causing damage there. The primary difference between fibrinogen and fibrin, it lies in their role in blood clotting and their structural states. So fibrinogen is this soluble glycoprotein that circulates in blood plasma, serving as an inactive precursor for fibrin. So like many other plasma proteins, fibrinogen is made by the liver. Fibrin, on the other hand, is the active, insoluble protein that's formed when fibrinogen is cleaved or cut by the enzyme thrombin. It's the cleavage that thrombin does, the cutting of fibrinogen that allows fibers to weave together and create a more stable blood clot, serving as like a blood band-aid on a broken vessel. The physical barrier of fibrin prevents further blood loss, and it also provides this scaffolding or like a skeleton for tissue repair. When a blood vessel is injured, the smooth muscle in the vessel wall contracts in a vascular spasm. This causes vasoconstriction, which reduces the diameter of the blood vessel, and it also reduces blood flow to the area, right? So we're limiting blood loss at the site of injury. The vascular spasm, it's a lot like a tourniquet, right? It's actually triggered by signals such as endothelin, which is a substance released by the cells that are lining your blood vessels when they become damaged. The duration of a spasm depends on the severity of the injury. It can be seconds to hours, but vascular spasm, it's the first line of defense, right? And it initiates the next two stages of blood clotting. In the next stage, the second stage of blood clotting, platelets start to adhere to the exposed collagen fibers in the damaged vessel wall. And so, like, as they're floating by, they're like, oh, hi. And the adhesion is mediated by something called the von Willebrand factor. It's a von Willebrand factor is a protein that bridges platelets and collagen, kind of binding them together. So when you bind platelets together, they become active and they change shape and they release chemical signals such as thromboxane. And these signals, they recruit more active platelets, and then those platelets create more, and then those platelets create more. And this leads to this humongous aggregation of platelets. And the growing mass of platelets, it forms a temporary platelet plug. This is sufficient to stop bleeding in minor injuries, but it's unstable without further stabilization. So it can only last for a little while. The very final step of hemostasis has its own substeps, of course, right? There's a lot more substeps than what I've shown here. All of these steps are part of a coagulation cascade, which is a series of reactions that basically turns fibrinogen to a fibrin mesh. Most of the steps of the cascade are simple enzymatic reactions where where a substrate is changed into a product by an enzyme. There are about 20 of these enzymes, and they're all given names such as clotting factor 5, clotting factor 6, clotting factor 7, and so on. All these clotting factors, they're all made by the liver. Types of hemophilia, bleeding disorders, are characterized by the lack of one, or sometimes more, of these enzymatic proteins. The cascade that has two pathways. So the cascade that can lead us to fibrin, there are two pathways. There's something called the intrinsic pathway, which is initiated by damage within the vessel, right? So things that are happening because of processes inside of your body. There's also this extrinsic pathway, which is it's triggered by tissue factor from damaged tissue outside of a blood vessel. Both of these pathways, they both use pathways of the clotting enzymes a little bit differently, but they all converge at the activation of factor X, right? They all converge at this point where they can activate prothrombin, make it into thrombin, and then thrombin can lead us through factor X. So all these pathways, they lead to factor X. And then thrombin can catalyze the conversion of fibrinogen into fibrin. So the resulting fibrin mesh, it basically like stabilizes the plug and it creates this really strong, durable clot to seal the injury site. This clot can last days until the vessel has time to repair itself. Yeah, I once had a student, we were talking about blood vessel or blood thinners, and he had the greatest comment. He's like, a blood thinner is water. He's like, that's what a blood thinner is. He's like, anything else that, quote, thins your blood is probably working on platelets, not the plasma. And it was just an interesting thought because it's most of the time when we think of blood thinners, we do think about coagulation issues. So blood thinners, which can also be called anticoagulants, they are medications that prevent the formation of blood clots, or they slow the growth of existing clots. They work by interfering with various steps in hemostasis, right? So they can inhibit clotting factors. They can reduce your blood's ability to generate fibrin or the ability to convert it fibrinogen to fibrin. All of these anticoagulants, they're often they're often prescribed to reduce the risk of serious conditions like a pulmonary embolism, like what we talked about, deep vein thrombosis, especially if you have varicose veins, stroke, AFib, and sometimes we might need anticoagulants when we have mechanical heart valves. Coumadin, warfarin, they're drugs that inhibit the production of a vitamin K dependent clotting factor. And there are a few of them, factor 2, 7, 9, and 10. Right? So warfarin prevents you from making these plasma proteins in the liver, and therefore it reduces your blood's ability to clot. Ampaxaban, no, I've never heard of that. That's Coumadin? That's Coumadin. That inhibits factor XA, which is an enzyme also in the clotting cascade. But again, I just thought that was a great comment that the student made. He was like, really, a blood thinner is water. So you need thinner blood, drink water. But in practice, it's not that simple.